Okay, let's go. All right, guys, so a bit of review on linear functions. First couple of examples are quite straightforward. Find the gradients of the following lines. Now what we're doing here, gentlemen, is making use of the fact that what we have going on here are really right-angled triangles. Okay, that makes it easy to calculate the gradient of lines when they're represented in this pictorial manner. So, of course, the gradient, you would realise from earlier years, is simply rise over run. I prefer to say it's the difference in y values over the difference in x values. Okay, delta means often enough in mathematics difference. So, making use of our right-angled triangle form here, I can see that to get from this point to this point, I've got to move 4 units in the x direction and 3 units in the y direction. So my rise is 3 and my run is 4. Now, the first thing I notice is that the gradient of this is either positive or negative. In this case it's positive because as we read it from left to right, it is rising. So we read lines like we read an English text. We read it from left to right, it is rising, so it's positive. So I'm not troubled by these negative signs or anything like that. Okay, so I'm moving across 4 and up 3. So my gradient here is 3 over 4, otherwise known as 3/4. In our second example, we're going to use exactly the same procedure. The M is rise over run, or difference in y over difference in x. Here I notice that the gradient is negative because the line is falling as we read it from left to right. Okay, so from here, here's my right-angled triangle. So I'm moving 5 units in the x direction to get from that point to that point, always using my axes where they're available, and I'm falling 10 units. So my gradient is quite simply 10 over 5, which equals 2. But notice it is falling, so it's -2. Alright? Okay, moving on a bit. Find the gradients of the lines that pass through these 2 sets of coordinates. Well, again, I'm going to say the gradient is the difference in y values over the difference in x values. And it occurs to me that you're used to seeing this formula from year 9. Okay, now there aren't too many traps here, but I like to start on the left-hand edge and go this way. M equals -3 minus 6 over the difference in x values is 2 minus -4. So in this case, M equals -9 over +6, and M equals -3 on 2. And I'm quite happy for it to stay in that form. I don't really want to see M equals -1.5. Now the only time you're going to run into problems here is if you inadvertently put your x coordinates, the difference in x coordinates, over the difference in y coordinates. The other thing to remember is that if you're travelling in the left-hand direction with your y's, you must be travelling in the left-hand direction with your x's. It's perfectly acceptable, and I might do example B like this way, to go right all the time. That's fine, you can do that, as long as you're consistent in the direction you are travelling. Because if you're not consistent, you can end up with the right numbers, but the wrong sign. Instead of positive, it will be negative. Instead of negative, it will be positive. Okay, so, example B. I'll travel rightwards in this case. M equals, it's always a good idea to write down a formula that's going to help you settle your nerves. That's the one I choose to use. So M is equal to, travelling the right way, or in the right direction, not as in correct direction, but right-wise, I'm seeing that I need to put in 1 minus -1.5 over 0 minus 6.5. Okay, so tidying that up, I get this. Sides together are the same, so that means plus. So -1 plus 1.5 is 0.5 over -6.5. Now that's a fairly unsatisfactory way of presenting a fraction. To put it in an acceptable fashion, I can simply multiply top and bottom by 10, getting rid of the decimal places. So that's going to equal 5 over 65. But of course that can be simplified too, and it's negative, equals negative 1 on 13. To repeat a point I made earlier, it doesn't matter where that negative sign goes, upstairs, downstairs, or right out in the middle, which is probably how a textbook would present its answer. So we did that sort of example. Finally, we can use the tangent to work out the gradients of lines quite readily. And we can do that because we can form a right-angled triangle over any interval. And this is the interval I'm choosing. I could have chosen that one, doesn't matter. It's going to have the same effect. It really doesn't matter. And so what we're doing is we're concentrating now on this right-angled triangle here. And we've got to pick a trigonometric ratio that's going to help us solve this. So, we're going to use the tan ratio. And we always end up using the tan ratio in these problems when we're finding a gradient. Now, the thing about the tan ratio, you'll remember from earlier mathematics, is that tan theta equals the opposite side over the adjacent. The opposite side over the adjacent. Now, but wait a minute, if I'm going from that point to that point, the y direction is the opposite side. The difference in y values is the opposite side. And the travel in the x direction is simply the adjacent side. Well, that's a handy relationship. That enables us to say, as easy as this, that m, the gradient, equals tan 15. And that's just a case of getting an answer from our calculator. So can someone please tell me what tan 15 is?
0.267.
And it goes on for quite a while, I expect. So is that rounded correct to 3 decimal places?
268.
268.
Yeah.
And we would say in brackets to 3 decimal places. Okay? So, that's our gradient. There. Let's have a look at this one. Not quite so straightforward. And we went through one of these last lesson. We can't sort of identify this as the right angle of interest, not directly anyway. What we're going to do is make use of this property, two properties. And the first property is that the angle sum of a triangle is of course 180 degrees. That means that, see the problem with using the tangent ratio directly here is that your opposite over adjacent is going to represent the difference in x values over the difference in y values. Well, that's not how we work out the gradient. Okay, so what we're going to do is simply call that 70 degrees, making use of the angle sum of a triangle formula. 20 plus 90 plus 70 is 180 degrees. Using the property of vertically opposite angles, this angle here must be 70 degrees. And what we're going to do now is use this right angle triangle as if I'm going from this point on the x-axis to that point up there at the tip of the arrow. Okay? So you can see that opposite is indeed our change in y values, and the adjacent is the change in x values. Opposite over adjacent, tan ratio can be used. Okay, so here we can simply say, oh, the other thing to notice is that our gradient rather, is going to have a negative value. All right, store that in the back of your head because it is falling as we read it from left to right, isn't it? Okay, so we just note in our brains that this has a negative gradient. And so we're going to say m equals negative tan 70. And our calculator is going to tell us that the gradient is therefore equal to tan 70. 3 decimal places will be good.
2.747.
2, 3 decimal places. Okay? Very good. And that's where we'll leave it for today. Thank you.